Good morning. My name is Brian Wilkinson. Thanks to Christopher there for explaining our product range today. And what I want to do is pick on some nuances that he mentioned to show you some facts that you may not know about our products and how flexible they actually are. So I'm going to show about the radiation-capable power supply solutions and how they fit with our concept going forward for space reference platforms and for applications solution focus. And I'm going to introduce this platform a little bit. It's just an example of a reference platform, and then look at the limits for RTG4 and good practices, and look at available component types for this, and how they can be adapted to use both for the space reference platform and also for the RTG4 device. A little bit about performance characteristics, and then we're going to look at the existing commercial solution that's applied to the development kit and some comments about that, and look to how we can rad hard or rad tolerant the solution going forward. So this is an example of a space solutions reference platform utilizing Microsemi rad tolerant and rad hard products. So you can see here we have the RTG4 evaluation card. We have a potential for a video card, an interposer card which connects the various different platforms together. LX7720 is a power driver, which can be used for motor drive or actuator drive as well, and incorporates a 4 half-bridge N-channel MOSFET drivers. And then the 7730 is a 64 single-ended channel telemetry controller, or 32 differential channels telemetry controller. The concept of this is to provide customers with the idea of how those could be connected together in one platform, and this may vary going forward over the next 6 months, but at least it'll show and demonstrate different applications that they can be applied to. On the left hand side it shows a potential power supply for this, and this is based on an SA50 that Christopher mentioned, and I want to just highlight some of the flexibilities of those components and how they can be applied in different ways. So just briefly, I'm not going to dwell too much on this because some of it you all know already anyway, but it's just to remind ourselves a little bit. Obviously the core power rail limits, power sequencing is important if the solution is not held properly, and then power estimator and some obvious decoupling practices for the design of the RTG4 card. So very simply, we have here our guest VDD 1.2 volts, the actual power supply for the charge pump at 3.3, and then obviously the power for various PLLs in different locations. And I want to come back to that a little bit. So we have some maximum ratings I think we need to consider for the VDD, for example, of -0.3 to 1.32, and then various recommended operating conditions. If we consider power up and down, power down sequences, as long as we hold a reset on the dev reset, then there's no particular requirement on power up and power down. However, if that is not the case, then please bear in mind the application AC439 design guidelines for powering up and powering down. And that also will apply to some later comments about the POLs. Decoupling capacitors, obviously keep decoupling caps close to the pins, use small size where possible, distribute them evenly around the device perimeter, and vias are important, particularly where you want to reduce the inductance. Inside the package we already have some precious metal electrode decoupling caps to help the PCB decoupling. and again refer to AC439 design document. So rad tolerant power supplies. We have a number of products here that we can consider, and the first starting point to check the power is in the actual RTG4 power calc spreadsheet, which is an approximation of the actual power requirement, a very rough approximation, but at least it gives you an idea of where you should be. And then obviously selecting the various devices to meet those requirements, either linear or in this case we want to talk about the POL isolated and non-isolated DC-DC, which we'll bring up shortly. So current requirements, this is an example for the calculator, and you can see with a 99% utilized device, 2 fast clocks, 2 slow clocks, around 496 IO with different types, and then 8 lanes of transceivers. That was calculated about 2.5 watts. But there is a very big range, obviously, depending upon if you hit the maximum frequency and the actual utilization of the device. And that could actually be easily up to 10 watts in pushing the performance of the parts. The RTG4 evaluation board block diagram, this is just an overview of how it fits, and if you have one already, you can see that in the actual manual and datasheet. And we have various power supply sections that are implemented at the moment in commercial solutions, and they work very well. And they were implemented to actually ease of design and to get the product out. But in terms of making this rad tolerant, then we need to look at a different direction. So here you can see the power scheme. There's basically a PMOS switch to turn the product on and off. There's 3 main devices actually driving many different kind of regulators, including, for example, an LX13043 linear device from Microsemi, and actually an LX7165, which is a hysteretic controller, which is quite interesting maybe in the future. So we'd be appreciated if you have any feedback on the type of control technology and topology that you're interested in. So Chris has actually touched on the SA50 already, so I don't want to repeat that again. One key point, however, is the methodology for control of the device, of the outputs. So we have a patented control technique, which basically is taking in voltage, it's recording voltage through an amplifier, and then giving a current to some in the primary of the actual transformer. What this actually means is that we get extremely good cross-regulation, and I'll just describe that a little bit later, because the application of this and the flexibility is extremely strong. So here you can see it's a little bit messy. SA50 series product, ER99 of course. And what I want to do is just highlight the fact that when I find it, there we go. Some of the characteristics. So we have very good line regulation. So for example, plus or minus 10 millivolts on the main rail, and 1% on the second and third rail, where it's a triple device. We also have quite good load regulation, and cross regulation is less than 1%, plus or minus 1%. And the ripple is extremely good for this kind of device. Looking at the application in terms of using it, I'll show you some flexibility features, which I think you should consider strongly in your designs. And also, as Chris pointed out, it can be used in different approaches. So it can be used, for example, with the different voltage buses, down to a minimum of 3.3 volts, for example. And this can give you a lot of flexibility in your satellite design. So I won't go through all this too much, but key features that are really important. Remote sense function, so the ability to regulate at the load point. This is quite a key feature, and is one of 4 which can help you to implement a much better power supply solution. Parallel operation, we can parallel up to 5 devices. So there's obviously rules around this on how you connect them with the parallel pin, but they work extremely well in parallel. In fact, we can series them also. The remote adjust allows you to adjust plus or minus 10%, basically by adding a resistor adjustment to go with the TL1431 or 431 voltage reference device, and you can trim this up and down by 10%. And then, of course, isolated sync input. So this is isolated by a transformer, and it means we can sync this to an external source. Even in parallel mode, you can sync one of the 5 devices if you want to sync, or you can sync all 5 of the devices. So this gives you ultimate flexibility for the actual solution. The series, Chris mentioned obviously the number, there's 28 parts here, and we do have 2800 and 120 and 50 volt devices as well. And as I mentioned, the single output and dual and triple output devices, 3.3 volts up to 28, but actually we're able to provide also custom with high voltage outputs as well, up to 6 types of outputs in one device. It comes in a standard can, which is easily mountable on a heatsink. We provide, or can provide, a thermal pad that matches this, and design guidelines to go along with this as well. So here's a really good example of, if you recall the space system reference design. So we put this in the block on the left-hand side just to show how flexible we can be to connect the actual products together. So here you see 2 SA50 50 volt input, 5R5 for the main rail, and 12 plus or minus 12 volts. You can see the 12, 12, 5 for both the devices. And we need a loading on the main rails of 5.5 volt of around 400 milliamps each, approximately, in order for the system to work correctly and to cross-regulate correctly. After that, we can connect the windings in different methodologies. So we have 3 12-volt rails connected in parallel for up to 100 watts. And then we can have one effectively 24-volt rail connected in cascade for, again, up to 100 watts. And the peak capability of these can be 140 watts each. But that's not continuous. It would be on a short-term basis. The very nice thing, and this is a good statement, power will automatically and dynamically distribute amongst the various loads. And that's due to the inherent cross-regulation characteristics of the actual product. This is a really key feature, and it enables your consideration for the partitioning of the design in different ways. So Chris presented this, so I don't intend to do this again particularly. There are some key features, as he mentioned already. What I want to show you is just the performance of the actual product, and go through a little bit about how this performs and some of the characteristics. So concentrating on the 2 devices that Chris mentioned, the 8564 and the 8565, these are actually rated at, I guess, 3 amps for the 65 and 4 amps, but that's after post 100K irradiation. So before that, they start off at 3.5 and 4.5 amps, and this is a low end. So typically, the device at 3.5 would be 5 amps nominal part. We can have a 12-volt input, as Chris mentioned, by 5-volt capacitors. I want to show you some characteristics under really low voltage when it's actually being used at 12 and 5 volts. Lower voltage outputs are definitely possible, and again, like the SA50, we have worst case analysis, applications manual and reports available, and so forth, which by request we can provide you. The performance of the device is clear. So we have plus or minus 0.5% line, plus or minus 1% load. We have extremely strong regulation over the say 1.2 volt rail at something like 20 millivolts maximum. And if you consider the RTG4, this has a plus or minus of 60 millivolts on the VDD, and also some of the characteristics of the transient for VPP, VPP, DL, etc. These are all maintained within this device. So we had many requests for setting the output voltage below 1.21 volts. So we can set this obviously higher than 1.2 quite easily using a resistor to set the value. But if we want to go below this, then we need to implement some kind of DC offset source and with an offset resistor. So we designed a circuit to do this, and you can see here the feedback configuration for going less than the V reference voltage. What we wanted to do is test this out and see how it would affect the overall performance of the product, and see if it would actually work. So I won't go through all this, but you can see there's an output voltage given by the feedback, by the resistor, etc. And we recommend that you don't go below 1 volts, and the reason for that is that there's some current fallback limiting, and the limit of the actual PWM switching frequency, it would be probably exceeded if you go below 1 volt. So we want to stay above that, and there's some resistance values mentioned here, and I'll show you in the next page most of the values, but you can have obviously this presentation. Another point is that it's a current source and not a current sink. So we need to be very, very careful about the actual minimum loading on this. So we actually did a calculation here, and you can see our load minimum is given here, which is based on an absolute minimum that you need to supply to ensure operation. So a little bit about the performance summary. And to verify this, we set a number of test methodologies in place, which is on the next slide, and we actually tested between 5 and 12 volts. So here you can see the component values versus the input voltage that's been set according to that equation. And the test performs, we've done load regulation up to 5 amps, line regulation between 4.5 and 5.5, or 10.5 and 13.5 for the different voltages inputs, an output noise and ripple, an output transient voltage, and turn on transient. So this report is available. I didn't put all the slides in because there's quite a lot of slides, but this is available by request, and we can send you that. This is a circuit. So we produced test PCB hardware and looked at the various tests to perform that I mentioned earlier. So what did we find? Interestingly, at 1.2 volts, obviously the device performance, as I mentioned earlier, is extremely good. And at 1 volt, we found at no load, for example, a peak V-out overshoot for example, 39 milliseconds, but then it returns very quickly to 1% of the regulated value. At the high current for the 5 volt input, the actual peak reduced, but the actual time for the overshoot was longer. And again, it returned to 1% of the regulated value. So for 12 volt case, we had slightly reduced at 240 millivolt peak overshoot for 32 milliseconds, and then back to 1%. And then iLoad, a similar kind of thing, reduced, much more reduced than the 3.5 amp 5 volt case, 150 milliseconds. But again, it went back to the 1% regulated value. In both cases, we recognize that the high current case, there was a significant activity of pulse during the turn on transient, which could have been indicative of the internal PWM entering a current limit, or in fact a maximum current pulse width limit regime, one or the other, or both. So the summary, the 8565 was tested under 5 and 12 volt conditions. We went up and beyond the 3.5 amp level to 5 amps. In all cases, the device actually worked quite well at V out at 1 volts, with consideration for obviously the turn on overshoot. The line and load regulation performance were absolutely very good and really compared well to the 1.2 volt output case. Degradation in performance was only observed at low current, and above 1 amps, the line and load regulation tracked pretty well between the 1.2 volt application. And all the remainder of parametric performance of the device was yielded excellent results itself. The ripple and noise and output transient performance were obtained for that, were very good also. So in our opinion, there's no reason not to consider this device in some applications. to run less than the V-reference voltage by implementing the correct offset solution. So paralleling devices, it's absolutely possible. We did not implement this on the 8565, but we implemented this on the 8564 by including some extra pins so that you can actually parallel the device. It's quite simple, so you just need to connect the VC pins together through a common capacitor to ground. And basically the devices will share current to within about 300 milliamps of each product. So they're quite good in terms of sharing current. The actual loop between all of them, there is a small offset due to the differences in tolerances for each device, but the output voltage will track the worst case reference voltage between all of the devices, which still means that they will actually give you the very good V-out performance itself. And there's no current hogging, basically because there's a negative temperature coefficient of the VC to the switch, the device itself, transconductance. So it doesn't current hog between the devices at all. So that can be very useful. You could make for example, 8 to 10 amp product using 2 devices, which is radiation capable to 100K, for example. And finally, the future direction, as Chris mentioned, I don't want to go in too much, but the SB30, the new proposed synchronous hybrid, also solution. But as you hopefully can see, there's many, many different solutions from the implementation of a few devices. Thank you.